how do we generalize this to n value functions? Well, it's actually almost exactly the same. So you can ask, why did it take 7 years for Deutsch to get generalized to Deutsch-Jose? And the answer is that if you read Deutsch's original paper, it looked nothing like this circuit. It looked quite different, and it was, I think, hard to generalize. And the other thing is maybe nobody was looking at it. So phase, oracle, and let's put a Hadamard on each of these places. And a measurement. And now what we want to do is say if f is constant, result is 0, 0, 0. If f is balanced, result is not 0, 0, 0. So the proof, the probability of getting all zeros is, okay, it's the square of the, I want to say this is plus to the log n, so log n pluses, tensor product of them, times f of, well, we have to put f as an operator here, and times plus to the log n. So why is this? Well, you're inputting pluses, and if they're all zeros, then the output had to be all pluses, because when you send a 0 backwards through a Hadamard, you get a plus. Do you have a question?
Are there any other cases where f is constant or balanced?
Yes, there's lots of cases that f is constant or balanced. For example, in the 2-bit case here, f might have been, 2-bit case might have been 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. Or rather, f might have been 1, 0 for this, 0 for this, 0 for this, 1 for this, which would have been, this is f applied to plus, plus. And this should be a 1/2. So probability of seeing plus, plus here is, well, you want to multiply this by the plus vector, or take the inner product of this with a plus plus vector, and that is 1/4 plus 1/4 plus 1/4 minus 1/4, which is 1/2. So if f is neither plus nor, if f is neither constant nor balanced, then the probability of seeing plus plus is neither 0 nor 1. But we don't care, because we said this was a promise problem, which means we only care about getting the answer right if f is either balanced or constant. So Yeah, so computer scientists have this, I guess, huge classification of different kinds of problems. And this is a promise problem because you only care about getting the right answer right if the promise on the input is kept. And it's also an oracle problem because f is given to you as an actual oracle. You're not allowed to look in this oracle and find the actual program that produces f. So this phase oracle is a black box. You cannot look inside. So yeah. So here, this is equal to, well, summation over x in 0, 1 to the log n. So all binary strings x. And I think I'd better put a 1 over 2 to the n in front of 1 over 2 to the log n in front of this because, well, because you need to normalize this vector and you need to normalize this vector. And normalizing them means you divide each of them by 1 over square root of n. So normalizing the whole thing means divide by. So that means when you take this, you divide by 1 over n. And this is summation. OK, am I going too fast? I think I'm going too fast. Let's step back. So plus to the n is equal to 1 over, plus to the, I guess, log n is 1 over square root of n times summation on all binary strings x. So do people see this? 0 plus 1, 0 plus 1, 0 plus 1, 1 over root 8. That's plus cubed. You take 1 from each of these things, and you take 1 of the entries from each of these things, so you get equals 1 over root 8, 0, 0, 0, plus 0, 0, 1, plus 1, 1, 1. And now, f applied to plus to the log n is equal to, well, it's the same thing. Sum x in all binary strings of length log n, f of x times x. So you take the inner product of this guy with this guy, and you get x times f of x. Because f of x is just a, f of x multiplies by plus 1 or minus 1. Actually, that's not quite right. This is the phase oracle, so it multiplies by minus 1 to the f of x. So let's call this minus 1 to the f applied to plus. And this is minus 1 to the f of x. And this should be minus 1 to the f of x. OK. So this is just the sum over all possible outputs of f, which if it's 1, if f is constant, then it's just all of these are either 1s or minus 1s. The whole sum is either 1 or minus 1. So this equals 1 in the constant case. And in the balanced case, half of these are 1 and half of these are minus 1. And it equals 0 in the balanced case. So that is a Deutsch-Joseph problem.